Good afternoon, everyone. Welcome to the panel Innovation Affecting CTBT Relevant to International Monitoring System, where we will be talking about the new sensor technology today. Thank you so much for joining us. Thank you very much for accepting to be panelists in this important panel. We are very pleased and excited to have you today. And in a science technology driven world, it's clear that one of our main mission to keep a close eye on emerging technologies and closely follow developments of particularly in new equipment, new instruments, new sensor technology. This organization needs continuously to be fed by science and technology. In the field of sensor, especially, is very important for us. And we know in your field, you are the expert, and some of you also developing some sensor, and then it's very important for us and for the audience also to know the new advanced technology, where we are and where we are going, what we need. We would like to talk with you. To maintain the IMS network high performance level and sustainability, we have been here doing some testing to enhance the performance of our sensor, our different sensor we have been using for technology, seismic, radionic, ultrasound, and noble gas and hydroacoustic. And we have been trying to test and enhance the capability, performance, and sensitivity of the instruments here. But in the same time, we would like to follow and focus the eyes to the others, new advancement in technology, to have it, to understand it, and to reflect it, to apply it in this IMS network sustainability. Thank you very much for joining us. And before we get started, let me briefly introduce panel members to the audience. Dr. Kodaira-san, Director General Principal Scientist of Institute for Marine Geodynamics, JAMSTEC, and also an adjunct professor in several universities in Japan. His main fields, crustal structures and dynamics of oceanic plate. Recently, he and his group in JAMSTEC have been developing seafloor, sub-seafloor observation systems. Welcome, Kodaira-san. Second, Mr. Professor Roger Waxler is a research scientist at the National Center for Physical Acoustics at the University of Mississippi. He leads the infrasound research group at the NCPA, and his main field is quantum field theory associated with solid-state physics. For the past 22 years, he has been focusing on acoustic signal generation and propagation in the atmosphere. Welcome, Dr. Waxler, and I'm very pleased to see you here today to know much about, particularly for the acoustic signal. And third, panelist Dr. Thomas Bruns is working as a scientist in vibration and shock metrology at PTB, the National Metrology Institute of Germany. He is the coordinator of the new pan-European projects INFA-AUB that aims to link the efforts of the IMS with those of the international metrology community. Welcome, Dr. Bruns. Fourth one, Dr. Geoffrey Crum, is a senior principal mechanical engineer at the Applied Physics Laboratory at the University of Washington. He led development of the 401 regional cable array mechanical systems and is currently active in the development of hydroacoustic systems, hydrokinetic power generation and storage systems, and seafloor geodetic instrumentation. Very interesting. Today also we had talks from Kodaira about geodetic instrumentation and the seafloor observation. Welcome. Dr. William Doucet is senior scientist at the Military Application Division of the French Atomic Commission. He is deputy head of the radio analysis, chemistry, and environment unit, and coordinator of the French Radionuclidic National Data Center. He has been working for more than 20 years in the field of nuclear instrumentation and environmental radioactivity monitoring. Recently, he has been involved in the development of innovative low-level detection next generation Spolax noble gas system. Welcome all and dear panel members. After introducing yourself, let's start our panel having your introductory remarks. As an answer to the, we had some question. You can explain your field of expertise and type of innovation that is, or maybe relevant to the International Monitoring System Network. We can start from Kodaira-san for the introductory remark.
Thank you very much. Maybe I'm gonna use my slide. Can I share screen? Sorry. Share screen. Share screen. Can you see my slide?
Yes.
Okay. Thank you very much. I'm gonna use several slides to introduce myself. As Nurjan introduced me, my expertise is a kind of marine seismology to study the subduction zone or seismogenic zone structure. But the scientist, my institute, is working very hard to establish new technology to monitor the earthquake tsunami at seafloor. So today I think I'm gonna mainly discuss about new technology to observe the earthquake tsunami and also geodetic data at seafloor. So, but before I'm gonna introduce myself, I first would like to introduce my institute, JAMSTEC. The JAMSTEC is a Japan agency for marine earth science and technology, and our kind of vision is to integrate integrated understanding of ocean, earth, and life. And in this institute, we have several divisions to study Earth's ocean life. For example, the global change study and also submarine resources and earthquake, tsunami, volcano, which I belong. I am a director general of the research institute to study earthquake and volcano. And also we have scientists who are doing so-called cutting-edge science, which include seafloor microbiology, and also we have scientists doing mathematical science and information science, and also we have very strong engineer group who are doing technological development of the ocean observation. So speaking about earthquake and tsunami monitoring in Japan, so we have very active subduction zone, and yes, the Japan is located a very complicated boundary, and we have Japan Trench and also Nankai Trough. And one of the important scientific target of my group is Japan Trench, where we got the magnitude 9 earthquake about 10 years ago, Tohoku earthquake, which generate a huge tsunami. Maximum height of tsunami is more than 30 meters, hitting northeastern coast of the Japanese island. And the other important target area of my group is so-called Nankai Trough, which is located southeastern western part of Japan, where we are very much worried about next magnitude 8 class earthquake and also large tsunami. This is the history of the magnitude 8 class earthquake in Nankai Trough, and the large earthquake occurred every 100 and 200 years. And then the very high large tsunami repeatedly hit Japanese island. And I just briefly introduce the kind of current status of the earthquake tsunami monitoring in Japan. So after the Kobe earthquake about more than 20 years ago, the Japanese government start deployment of the very high densely deployed network, seismic network on land, like you see on this map. The dot indicate the seismic station on land. And also after the 2011 Tohoku earthquake, the CIFRO network is developed to monitor the earthquake and tsunami offshore. And this is very much key infrastructure to make early warning of the earthquake tsunami. And for example, in northeastern part, offshore northeastern part of Japan, where we observed the Tohoku earthquake, the Japanese, one of the Japanese institution, NIED, they deployed 150 stations of the cable embedded seismometer, so-called inline type of the seismometer and pressure gauge to monitor the earthquake and the tsunami in Japan Trench. And also we JAMSTEC developed the node-connected seismometer pressure sensor and hydrophone array in the Nankai Trough. And after we completed to construct this network, the now NID is operating this network. And the point is the seafloor observation is very much key infrastructure to make accurate and quick early warning and earthquake. And I briefly introduce key infrastructure or technology which we JAMSTEC have developed. That is DoNet station in Nankai Trough. As I mentioned before, DoNet is cable connected node type observation or seafloor observation system. And we have several scientific node to which we connect several sensors. And the important kind of concept of DoNet network is reliability, redundancy, and sustainability. And I think most important concept is sustainability. As I mentioned, we have the scientific node in this system, which allow us to replace the sensor when we make a new technology, new sensor or something happen in the sensor. This system make it easy to replace everything. And as I presented in previous session in this meeting, one of the important research project which we are doing in this subduction zone is to construct real-time continuous seafloor geodetic network using a DoNet cable system. And to do that, our team has been installing a borehole observatory, which includes seismometer, tiltmeter, and strain meter, and pore pressure gauge. And also, we are now trying to utilize a tsunami sensor as the geodetic sensor to monitor the vertical seafloor displacement. And also, our team is now deploying the fiber optic sensing system at seafloor to connect the DoNet cable system in order to obtain the real-time continuous data from fiber optic cable. So our system development group they are doing several type of fiber optic observation, including optical tilt meter and also a string meter and a DAS system to monitor the tilt and also broadband or earthquake signal and also long-term strain change and also high density hydroacoustic signal and also micro to large earthquake. And then at the same time, in order to fully utilize the seafloor geodetic data, the another important scientific challenge is to make a 3D seismogenic zone structure. So to do that, our team in Jamstack is doing our seismic imaging to obtain the 3D structure just below the seafloor network. So this kind of seismic imaging of the interior of the Earth using active source seismic data is kind of my specialty. And what we are doing right now is to acquired 3D seismic data to make a realistic 3D model just below the network along the plate boundary subduction fault. So this is everything what our research group doing in Jamstack. Okay, thanks very much.
Thank you very much, Kodaira-san.
And stop
Introductory
sharing.
remarks. I would like to give floor to Professor Roger Waxler. We would like to hear your field of expertise. Please, floor is yours.
Okay, I'm loading my, there it is. Loading my screen. And do you see that?
Yes.
Do you see my slides? Yes.
Yes.
Okay. So I work at the National Center for Physical Acoustics at the University of Mississippi. We usually say NCPA. I lead the infrasound research group, and field theory and solid state physics were left behind several decades ago. In my group, we have several people that have different expertise. Carrick Talmadge leads the hardware efforts, sensor design, and sensor metrology, really, not just calibration. The Hyperion sensor was designed and prototyped here, and the university licenses the technology to Hyperion. And Hyperion has made improvements, to be sure, but the sensor was developed here. Carrick has worked hard on laboratory sensor calibration. He developed a calibration tank that he instrumented and became functional and has used it extensively. We sold one to Sandia, so now they're using the same technology, and Hyperion has developed one for themselves. I don't know if it's up and running at Hyperion yet. But laboratory techniques for broadband infrasound sensor calibration were developed here. Not the first approach, of course, but it's the approach that's now, at least in our circles in the States, considered state of the art. Propagation modeling and signal generation is really my expertise. We have released an open source package that is constantly undergoing upgrades. At the moment, we have some funding to do upgrading. We've done some serious upgrades on it. a new version will be available soon. Uh, Phil Blom, who's at Los Alamos, was a student of mine, and so I'll take some credit for his extensive work. But geometrical acoustics was the tool he used here, and he then took that expertise to Los Alamos and expanded on it and developed a geometrical acoustics package that's also open source, that's widely used. It's called InfraGA. And again, both packages are under continual improvement and development. Garth Frazier leads our signal processing effort. He actually comes from an electromagnetic community, but he transitioned to acoustic processing probably about the same time I transitioned to acoustics, about 20 some odd years ago. He's been working lately on large N. I'll have a lot to talk about, and it means many sensors, array processing for noise mitigation, subspace methods for multiple source detection. It hasn't been published yet, but I'll say he's recently extended the music model to be applicable to infrasound by allowing for different noise levels at each individual sensor. And he's an expert at real-time data analysis. That's actually what he cut his teeth on. Richard Raspet, who's recently retired but still comes in to the lab every day, did a lot of what I consider really beautiful work on wind noise, where he and several students figured out the physics of wind noise generation. I wrote here to inform array placement and manifold design, and that's true. That's what we use it for. Manifold being wind noise reducing manifolds. But through a series of experiments and a bunch of theory, they've isolated what components of the atmosphere actually produce the noise that contaminates our sensors. So rather than keep talking about what we do, I will talk about what I consider to be the status of ground-based infrasound sensing technology. A lot of progress has been made in the last decade. I think we in the infrasound community benefited from the state of the technology 20 years ago, where it had sort of been ignored for some time. And so it was clear there was a lot of work to do. And so a lot of people worked hard. And currently we now have high fidelity sensors. They're stable, low noise, low seismic sensitivity sensors are available. Sensor calibration is reaching maturity, not just the laboratory calibration that I referred to that Carrick was involved in, but in situ field calibrations, a method pioneered by Tom Gabelson at Penn State that allows us to actually calibrate the response of the sensor in the field, including the response of the environment in which it's deployed. So in my view, that's huge. You have a frequency response curve across the relevant band for the sensor response as it's deployed, rather than just a laboratory response. And international standards for laboratory sensor calibration are under development. There's an international group that's been meeting the past few years. And the in situ field calibrations are becoming standardized. I'm not really up to date on what's been going on, but the CTBTO has sent teams out to perform these calibrations at many of the infrasound stations. In my view, the two big problems, the biggest one is wind noise. So this is really the only plot I've got here. This is just the raw signal. It's filtered only by the instrument response of one of our sensors, one of the Hyperion prototypes that was just put out in the field in 2010. We were doing some hurricane studies. And this is just the signal over several days. And you can see that, oops, I went back, sorry. Let's get it back. Technology. Where is it? There we go. I apologize. Uh, you can see these quiet times, that's nighttime. These loud time, that's daytime. And so what happens at night, the ground cools and it presents a stable environment to the atmosphere. Turbulence is suppressed by the temperature inversion. In the daytime, the sun comes out and the ground actually acts more or less like a hot plate, causing the air to appear to boil more or less. And that generates large turbulent structures in the atmosphere. And you can see that the difference in the noise is huge. It's probably about 40 to 60 dB. And so you see night, day, and then this nighttime where it's a little louder, there was actually a storm passing through. But you can see that the storm noise is actually even much less than the turbulent noise that gets generated during the daytime. Since we can't guarantee that nuclear weapons tests are going to be constrained to the night, we have to deal with the atmospheric noise levels that occur during the day, and they're huge. They depend on the environment in which the station is deployed. Island stations are notoriously difficult because there's wind across the sea, and the difference between day and night is not as extreme on an island because the solar heating, if the island is not too large, the solar heating is not so dominant. And to me, this is the largest impediment to signal detection, dealing with this wind noise. There is a traditional methods for dealing with the wind noise by enclosing the sensors in some sort of wind noise reducing manifold. The CTBTO stations, many of them have these pipe arrays. They tend to provide about 20 dB signal enhancement. That's roughly 1 over the square root of the number of openings in the pipe array system, and other wind noise reducing manifolds. Typically, the best you can do is about 20 dB, and it's not sufficient in windy environments. So for me, dealing with this wind noise, increasing signal to noise, you have to be careful not to decrease signal as you're decreasing noise, of course. It's the signal to noise ratio that's critical. And in my view, that's one of the main problems that we have. The other problem is that the IMS network is sparse. If I did my arithmetic correctly, without a grad student to help me, it's about 2,000 kilometers per station on average. And in addition, infrasound propagation is quite directional due to its dependence on the winds. And so that further limits the density of the effective density of the network. And the obvious recommendation, which I guess is less technical than political, is to include auxiliary infrasound stations in the monitoring processes in the same way that there are auxiliary seismic stations. So here are my recommendations. Wind noise mitigation. I believe that the what's coming over the hill are large N arrays. So several groups are working on the development of low cost, low power sensors that have enough fidelity so that you can actually use a lot of them in an array, and they're well matched so you can do signal processing to improve signal to noise. This technology is under rapid development. There are several groups and companies working on it. I'm not going to go into who or what. It's, in my view, it's 3 to 5 years off from getting close to a commercial device, but I think that's the future. I think that's the only really effective way to deal with the wind noise problem. Well, unless something else comes around the bend that I can't foresee. I mentioned auxiliary infrasound stations, the large-scale experiments that have been done over the past decade. A few IMS stations pick up the signal, but to really get good localization, either seismic stations or some of the research arrays that are now being deployed across the world are used. This goes beyond sensors and hardware, but it seems to me that adding realistic propagation modeling capability would aid in localization and signal association. And these models are under rapid development. The math is sort of understood, And what's happening now is algorithms are being tightened up, and speed is being improved, and parallel processing is being brought on board. Hardware improvements in computation are being brought to bear. And so I think this is something that might be important in the near term. And something that's, in my view, critical is to get a real physical handle on uncertainties. So the atmospheric sciences community, so for infrasound propagation, the medium is the atmosphere. And we lean on the atmospheric sciences community to provide us with the wind and temperature profiles in the atmosphere that we use to characterize the medium that we propagate through. The development of such models in the atmospheric sciences community is currently rapid. We're in a period where a lot of work is being done on that, and it's being improved every year. And uncertainties are now becoming available in the sense of really ultimately probable distributions, statistical distributions of profiles from which you can propagate the errors into your propagation model, so that uncertainties based on physics of the atmosphere and that have a rigorous statistical basis will probably be available within the next 5 years or so. And I feel it's critical to get these uncertainties into localization and association algorithms. And that's what I have. Thank you.
Thank you very much, Professor Waxler. We have many common topics. We have been also trying to improve our ultrasound stations, adding on-site calibration capabilities, and also wind noise reduction system, which you may also know. I'm very pleased also we have been developing a new sensor, Hyperion. We're also going to use it, and already we had some set of Hyperion. Thank you very much. It's very interesting. Your field area, very common with what we are doing here with CTBTO. And next, Dr. Thomas Bruns, I would like to also hear from you, your field of expertise. If you present us, floor is yours.
Thank you very much, and welcome from my side. I also will try to share my screen. It works. You can see it?
Yes, we can see.
Okay, maybe I start with a kind of apologize. I'm not really a member. I'm more a newcomer to this community and probably to your audience as well as to you. I have some thoughts and some connection now to geoscience and to the CTBTO work. But to understand my thoughts, I think you need to understand my background. And therefore, I would like to start with an introduction to, let's say, my daily work or my institute's daily work. So I call the presentation, the slides, an introduction to PTB and metrology. We heard several of the terms I'll be using already, for example, in Roger's presentation. But I think I'm talking about a different route and a different kind of quality of thinking about the matter. You will see what I mean. So where am I coming from? I'm coming from Germany, from the National Metrology Institute, metrology being measurement science, not the weather science. The National Metrology Institute of Germany has two main locations, one in Braunschweig, where I'm currently staying here in front of my desk, which is the major site, and a co-location in Berlin, which is the original site. And there's also a highly specialized campus on radiation metrology, also in Berlin, but not at the same place as the original site. So in Braunschweig, we have about 1,500 employees, half of them being scientists and engineers, and 6 science divisions, of course, a lot of administration and stuff. and a large but very nice area that you see in the aerial photograph. In Berlin, of course, it's much more crowded. There are 2 divisions, science divisions, and about 500 employees with the same ratio of science and engineers, among others. In order to introduce me and my work, I would like to explain to you what the National Metrology Institute actually does. And among the many services we provide to society, the industry actually, and also the government and science, the scientific community, I would like to focus on one special branch, which is usually called realization and dissemination of the units. And the units means the International System of Units, the SI. And in order to make it easy to grab, I use the most prominent examples and then the example where my daily work actually comes from. So I think the most prominent example over the last few years was the example of the mass scale. You may have heard about the redefinition of the kilogram. And this was actually 2 or 2.5 decades project in PTB, as well as in other institutions like the NMIJ in Japan, for example, or NIST with a watt balance in the US. And here on the left, you see, well, the artifact that was realizing the kilogram for more than 100 years, which is the kilogram prototype, or in fact, what you see here has the number of 52 on it. It's one of the national copies hosted in Germany of the International Kilogram Prototype, which is held in Sèvres in Paris in a safe somewhere in the cellar of the BIPM. So this is the realization of the unit, or was until 2018, and nowadays the realization is more abstract, being implemented in the watt balance, for example, or in the silicon sphere that you see in the right picture, where actually by counting the number of silicon atoms in a monocrystalline sphere of known dimension, you define what mass a kilogram has. So this is one nice thing to have. This is realizing the SI unit of mass, but then you have to disseminate it. And dissemination for this unit is simply done by calibration. So we heard already from Roger about calibration of instruments, but this here is what we call the traceable calibration. So we calibrate kilogram artifacts from calibration laboratories against our realizations of the kilogram. So we compare on a weighing balance the silicon sphere more or less to a kilogram prototype of a verification office or of a calibration lab. That is under strict quality control. And we always give them their number, what is the mass of your piece of metal you deliver for calibration, but we also give them an uncertainty that is validated. So you know not only the measurement value, but you also know with what uncertainty you have this value, and you can calculate with that uncertainty. Another very prominent example is the national timescale. By the way, that's the same in all, more or less, all national metrology institutes all over the world. They all have these tasks and fulfill them in a very similar way. So at PTB, we operate this atomic fountain clocks. You may have heard about devices like that. There is a cesium fountain inside where cesium atoms are excited and pushed towards the sky for about 1 meter of rise and then free fall again. And in between, an electronic transition frequency is measured, and the clock, a clock running synchronously is adjusted to that frequency. So this is the realization of the second as the unit of time. Again, it's nice to have those devices in the laboratory, but you have to distribute it to the public or to science in order to make it available and to make it useful. And one of those distribution systems you all know, it's called NTP, Network Time Protocol. It's not here on the slide. Unfortunately, I forgot to mention it, but of course, PTP is running 3 NTP servers that you can connect to easily from all over the globe. And you can get the exact time. And if you call my colleagues at PTP, you can also get the information about the uncertainty of this time. Actually, there is software around that can also include you the uncertainty of your network connection. Another well-established distribution method is radio-based. It's called DCF77. It's a 77 kilohertz radio signal distributed from the central place in Germany, close to Frankfurt. And although it's quite an old system, it's still used a lot, many clocks. And actually, we cannot count how often it's used because you do not have feedback from the users. But it's far from being obsolete by NTP. So I think everyone has encountered the one or the other of these kinds of realizations and dissemination actions from national metrology institutes during his lifetime. Traceable in this system means that coming back to the kilogram, if you go to your supermarket and you use a balance there to weigh your vegetables or whatever you buy, usually this balance has been calibrated or verified by some authority, and this authority has calibrated weights applied for this calibration, and these calibrated weights then have a traceable link to the national standard. And not only the value, but also the uncertainty is traceable to an uncertainty given by the national standard. Of course, along this chain of traceability, this uncertainty is increasing. Cannot get better than the institution one step up in the ladder. So, and the same is available for acceleration or velocity for that matter, as it's the integration. And this is actually my field of expertise and my daily work. I'm not only head of the department here for acoustics and dynamics, I'm also the head of the working group for realization and dissemination of acceleration. And what you see here is the most used acceleration standard that we have in the laboratory. What we do is we apply a sinusoidal excitation to an accelerometer under test. So this is actually just a calibration device. And we measure the displacement that we apply to this sensor by laser interferometry. And actually, we can measure down to fractions of a nanometer, which is necessary if you want to calibrate at, let's say, 20 kilohertz, which is currently the upper official limit of our calibration systems. So we measure this displacement or the movement of the sensor by laser interferometry with 2 interferometers, because you always apply some rocking motion and tilting and stuff, so disturbing motions to the sensor. And because we know the motion over time, we have tracked it traceably by the wavelengths of the helium neon laser. We can calculate the acceleration acting on this transducer, and we can measure the output voltage or charge, if it's a charge type transducer, and then put it into relation. So we measure effectively the transfer function over frequency of such transducers. And we provide it to our customer with a given uncertainty, which is currently in the best case about 0.1% relative uncertainty, which is more or less also the global limit for such calibrations. And although this frequency ranges and the size of the device is not really related to CTBTO, we also have other devices like you see it here. This is a multi-component calibration device that we for example, used over the past years to calibrate seismometers. You see here on the left, CPZ seismometer from CEA in France that's mounted on a 3-axis shaker table. And I don't know whether it's visible to you. If you look very closely here, behind the adjustment screw, you see a red dot. This is the helium neon laser pointed at a reflective tape. So we measure here also with helium neon lasers on the right here in the left upper corner, you see one of those devices. We measure here in 3 directions the motion of the sensor and calibrate it. And again, provide calibration certificates, including uncertainties, validated uncertainties to our customers. In my world, let's put it this way, in my usual community, we work a lot for industry, but nevertheless, a map like that on the left-hand side may be familiar to you if you think about the dots as geoscientists' monitoring stations. In this case, however, it's accredited calibration labs. So that means those are places where laboratories have their traceability linked to PTB and are accredited in terms of their methods, their systems, and actually their staff are under quality assurance and quality monitoring by on-site assessments. And on-site assessment is also a term well known in the IMS terminology. So we have a traceability system established on a national scale, starting at the National Metrology Institutes, going via those accredited calibration labs into the industries, in industrial calibration labs, no longer accredited, and into the measurements in production or in the product, if you think about the sensors nowadays available in an automotive device in a car. And the interesting thing about that is you can do comparison measurement in either of those laboratories. If you send them the same instruments and they calibrate it, giving you the value and the uncertainty, the results should be consistent within the measurement uncertainty. And they are. We do regular comparison calibrations in this system to prove that the quality is all right. And similar systems are, of course, established in many other nations. In Germany, the accreditation is called DAX, and the community of the accredited labs is DKD, the German Calibration Service. In France, it's COFRAC. In UK, it's UCAS, or in the US, there's A2LA as an accreditation body, and there are, I think, at least 1 or 2 others. So similar systems exist all over the world. And the interesting thing in the background is that they are not only existing in a nation, they are also linked. So there is a kind of mutual acceptance between those measurements and calibration systems in the individual nations. I just put here as an example PTB and NPL, the National Physical Laboratory in the UK. But you can place here any calibration hierarchy in any developed country in the world. And they all are subject to the CIPM MRA. This is the CIPM Mutual Recognition Arrangement, which applies or instantiates instruments, basically key comparisons between the national laboratories to make sure that calibrations in Germany are comparable and consistent with calibrations in the UK or in the US or in Japan. We had comparisons with NMIJ, for example. And within our stated uncertainties, these measurements are consistent. They give the same results. Of course, not exactly to the point of the value, but within the measurement uncertainty. And this CIPM MRA is an international treaty. So there are signatory states, I think around 130 by now, signatory institutes actually. And it's an international treaty about the mutual recognition of the calibration result, and therefore also about the measurements with those calibrated sensors. And then there is an international organization for accredited calibration labs, and they adapted this MRA. So also the national calibration laboratories, industrial-wise, are linked internationally to this system and are covered or backed up by this international treaty. And I think this is a very important and actually a new thing to the IMS system. And this is my proposal, like Roger pointed it, or my idea, what may have a major impact on the IMS system within the next years. To get all those sensor stations actually traceably linked to the SI, through the international system of units, and actually backed by this CIPM MRA. Because if your seismic station, for example, or your infrasound station is traceable to your or some other national metrology institute, you're automatically backed up by the CIPM MRA for this calibration. And I think there's actually in this also politically sensitive area of the CTBT, there's nothing better than having an additional and scientifically oriented international treaty to back your measurements up. So I think that's one of the important next steps. As far as I understood, only very few station operators are currently going in the direction to gain traceability. There are some efforts. I come to this on my next, which is the final slide. But I think it's important. And Nurcan, you also asked for the readiness of this technology. I think with the industrial background I showed you, I already indicated that the infrastructure or the formalities are already there. This is not a problem. Beyond that, we have some actions in the background. I just looked up the BIPM, which is this institution in Sèvres that in Paris, that where all the metrologists worldwide are coordinated, you may say, and where the CIPM MRA has its location, its root. And there's a news message just now that CTBTO and the BIPM, or the CIPM as the highest ranking committee, are actually taking up relationship. And I also learned that the CTBTO is now a member of the Consultative for Ionizing Radiation, which is the highest ranking scientific committee in the metrology area about ionizing radiation and all the metrology around it. Beyond that, we have currently a research project running, which is called Infra-AUV. You see the link at the bottom of the slide, where we develop our own systems further on so that we can cope with the demands from CTBTO. So currently I showed you this 3-component exciter in my laboratory. Since a few weeks back, it was not capable to go down to 10 millihertz for measurements and calibrations, but now it is. So within this project, we extend the frequency range to cover those ranges which are not really used by industry, but which are very vital to the IMS or geoscience measurement stations as a whole. So that's my contribution here. Maybe one last remark towards Roger. I would be very interested in getting in contact with the people you named about on-site calibration, standardization of calibration, because from the metrology side, we have a lot of standards for calibration, laboratory calibration. And before we start something in parallel, we should join forces, I guess. So thank you.
Thank you very much, Dr. Bruns. It's really interesting. Of course, we should know what we are measuring against what. This is very important point for. We have been monitoring more than 90 countries and using different UIs, different sensors. But you said multi-component calibration device you have been using and already developed. But every device and every sensor has its own frequency range. Then I did not quite understand how come the one multi-component calibration device can calibrate all the devices. Anyhow, we will going to discuss about this, but it's very interesting. I really celebrate you. It's very interesting subject also. Then we are going to go, Dr. Kram, Geoffrey Kram, for to have his introductory remarks in his field. Please, floor is yours.
Well, thank you.
Geoffrey.
Yeah, thank you. I'm going to start purely verbally at this point. I do have some slides I will show, but would like to introduce my institution first. I work for the Applied Physics Lab at the University of Washington. Now, Applied Physics Lab or labs or applied research labs are institutions across the United States, typically affiliated with one branch of the armed forces or another. Our initial association and continuing is with the US Navy. We were formed in 1943 to help them solve a technical problem, and that worked out fairly well. And we continue to work with the Navy, developing a strong expertise in underwater acoustics and branching out in other areas. At this point, perhaps, we have about 250 employees, almost all of them working at the University of Washington. We are a very strongly vertically integrated organization. We have a large number of scientists working on theory and applied science. We go on many oceanographic cruises every year. We do a lot of work. We continue to do a lot of work with the Navy. We probably have 40 to 50% of our budget comes from US Navy funding. But we also do work for the National Science Foundation. That's probably our second largest client base. We've been consulting a bit with the CTBTO. We have Microsoft as a client as well, and numerous other organizations. I started about 11 years ago. I joined the Applied Physics Lab at the start of what's known as the Regional Cabled Array. At that point, it was a concept, and we worked very, very hard to actually build this system. And what it is a cabled undersea observatory similar to Ocean Networks Canada, coming out of Vancouver Island. In our case, we have two primary cables that are telecom grade cables, both entering the ocean at the Central Oregon coast. One of them goes about 500 kilometers to an active undersea volcano. And then the other one heads out parallel to the first one at first, then heads south, goes down into the abyss, and then back up onto the continental shelf, ending at about 80 meters depth. And strung out on these two cables are a number of nodes, scientific nodes, and attached to those nodes are a wide range of scientific instruments, a number of commercial oceanographic instruments, as well as a number of custom developed instruments. So we have currently we have something like 140 instruments on this cable, all reporting back in real time. So we have, including in those, we have seismometers, we have hydrophones, we have tilt meters, and this is where my interest is primarily these days. I led the mechanical development of the secondary instrumentation systems on there, the platforms in particular, and a very successful autonomous profiler that lofts instruments up and down the water column 9 times a day for a year at a time, all reporting back in real time. But what I'm doing in recent years is working a lot on geodetic systems. We're in an active area, not quite as active as what what the Japanese are experiencing, but we also have our own subduction zone. So we have geodetic instruments attached to this, specifically tilt meters and seafloor pressure sensors, bottom pressure sensors, to detect the vertical movement up or down of the seafloor in seismically interesting areas. So the technology for the instruments that detect the position of the seafloor, those instruments are based on pressure sensors. We have 1 atmosphere titanium housings, inside of which we use a commercial pressure sensor. They're very good. They're made by Scientific, and they're freakishly precise. But they have one characteristic, which is long-term drift. And historically, people would go down there once a year with an ROV, and they would do an in situ calibration to subtract that drift to be able to, in effect, recalibrate the instrument. Now we've developed systems whereby we actually switch that to the internal pressure of the 1 atmosphere housing, and allows us to correct for the drift autonomously, if you like, or in response to a signal from shore, not having to visit the device at all, allowing us to be able to measure seafloor position to an accuracy of millimeters to perhaps a centimeter or so at depths of 2,000 or 3,000 meters. And we can do that stably over the course of a year by virtue of periodic recalibrations, where we essentially reset the zero on this thing. We have a similar approach to measuring seafloor tilt, where we're looking at resolutions on the order of microradians, and we do that with a three-axis or tri-axis accelerometer from the same outfit, Scientific. It also suffers from the same drift problem, but it's definitely addressable by actually rotating the thing. We have stepper motors inside the housing that rotate it to establish where the zero is, and then subtract whatever drift has arrived, has resulted in the intervening time. And with that, we also have a great deal of success. We're quite happy with that. The topic of interest that I have at this point is what is commonly known as distributed acoustic sensing. We have lots of experience with cabled systems undersea, and those cable systems, in a lot of cases, have optical fibers in them. And Kodaira-san referred to distributed acoustic sensing with respect to the work that JAMSTEC is doing. And we are starting to look very hard at that. We've recently set up an institute within the University of Washington, the Earth and Space Science department has, to look more closely and to bring in more distributed acoustic systems, sensing systems, and to see how we can apply them at the Applied Physics Lab and with the School of Oceanography, to see how we can apply them subsea. There are a lot of possibilities here, but I think what I'll do is I'll work on sharing my few slides. And could someone let me know whether you can see my my slide? Yeah, okay, good. So distributed optical fiber sensing, I guess, is probably the overriding generic term for ways of using optical fibers as sensing elements in their own right. And what we're talking about here is commercially available equipment. The electronics that's used to start all this stuff off is something called an interrogator, and it contains a laser that sends out pulses of light, very carefully calibrated at frequencies, typically in multiple kilohertz, and it sends these pulses into an optical fiber. And this is technology, by the way, that has been developed over the last 40 years. So in some cases, it's really quite mature. But if you have an optical fiber and you can attach an interrogator to it, you can essentially treat that fiber as a series of distributed sensors in their own right. And discontinuities or scattering features within that fiber send a small percentage of light back, which is received by a detector within the interrogator. And a whole bunch of electronics inside there and some clever software will allow you to detect environmental conditions around that fiber. And you can imagine how this would actually be useful for systems underwater. And, oh, by the way, there's another aspect of this that's particularly interesting. Because these pulses are at very carefully timed intervals, you can use the time of flight to actually indicate where in the fiber your discontinuity had happened, and consequently, you can address individual sections of the fiber and know exactly where they are to find out what your signal of interest, where it originated. So there are three principal technologies there that are being used these days, but the one that I find the most interesting is based on Rayleigh backscatter, which is where you have an interaction between the incoming photons and refractive index variations within the fiber. And those variations are frozen in as the fiber is formed in its original manufacturing. They don't change. And this is a very elastic collision, so energy is preserved, frequency is preserved, polarization is preserved. You can use this to measure temperature and strain. And by the way, this is what's formally, or this is what's colloquially referred to as distributed acoustic sensing, or DAS. Schlumberger has called it distributed vibration sensing, and there is a move afoot to try and make this a little bit more generic and call it distributed Rayleigh sensing, but they're all essentially the same thing. And what's interesting about it is you can get very nice temperature resolution down to 5 millicelsius. Spatial resolution, meaning you can address segments of fiber in segments of 1 to 20 meter spatial resolution, and you can do this for 100 kilometers. And you can be checking measurements or getting the data back in hundreds to thousands of hertz, depending on the particular circumstances. So it's already quite commonly in use. The power industry uses it to measure temperature and strain on their power lines. Onshore and offshore boreholes are instrumented this way for seismic measurements. Borehole flow, they use acoustic measurements to indicate flow as well as temperature variations. They're burying these fibers horizontally under the earth it can make them sensitive to seismic signals. It's it's obviously would be useful for perimeter surveillance, and pipeline monitoring as well. So it has pretty strong characteristic is it's has a very high update rate, and it's extremely sensitive. So how might this possibly be applied to the IMS? Well, the hydroacoustic network, and this is an image from the IMS folks, is made up of a number of T-phase stations, which are seismometers, and hydroacoustic stations, which are triplets of hydrophones suspended in the water column. And whoops, these red dashed circles are the 6 hydroacoustic stations. 5 of them have actually 2 triplets, one on either side of a remote island. And the 6th one has only a single triplet, and it's coming off Cape Leeuwin at the southwest corner of Australia. And a typical hydroacoustic system will look like this. There's a shore facility on the island, or in the case of Cape Leeuwin, on the mainland. There's a cable. This is a telecom cable, so it's a steel strength member, which also happens to be the conductor. And inside it are a number of optical fibers. And that goes down to a hydroacoustic node base, and that can be anywhere between 21 and 215 kilometers of cable away from the shore facility. And up, suspended above the node base is a float with an electrical cable with a hydrophone in the middle, and that's positioned within the sound channel. 2,000 meters of cable later, there's an identical system, and 2,000 meters later, there's the third one. So in effect, this forms a triplet useful for detecting large underwater sounds. So clearly, nuclear explosions factor into that. But it turns out they can also pick up other things. The ARA San Juan submarine disaster was detected in this manner. Earthquakes can be heard as well. I believe even sea mammal sounds can be heard. One of the things that is of interest here is the fact that this first length of cable from the shore station to the first node is it contains optical fibers, and that would lend itself very well to hydroacoustic or seismic detection using a distributed vibration sensing system. So if we were to put an interrogator in the shore facility, you could use this cable without affecting anything else. I believe there are dark fibers in most, if not all, of these installations. So you could use fibers that are not otherwise being used anyway. And you could pick up seismic signals, you could pick up acoustic signals, temperature, and potentially strain as well. And if you got really enthusiastic about it, you could put in an interrogator, you would marinize it and put it at the base of the first node. This obviously couldn't happen until and unless any of these nodes were to be replaced. And you could modify these riser cables instead of being purely electric to have the optical fibers within them. And in fact, you could make a continuous optical fiber going up and down the first two riser cables, and then up the third riser cable, all attached to one interrogator at the base of the first node. And that would allow you to also pick up acoustic signals within the area of the cable, particularly the area within the sound channel. And given the fact that you have a number of independently addressable segments there, you could imagine doing some interesting beamforming with that as well. And that is the extent of what I have to present technically. I believe there's some other questions there, Nurcan, but I will wait until you ask me or ask us to address them specifically.
Thank you very much. It was really also interesting. Your field was also interesting for me, but it's good to a bit direct an approach to the geodetic system, which we really understand more about Earth and seafloor deformation from geodetic system. And the next one is Dr. Doucet, Wilhelm Doucet. We would like to know also your field. Please, floor is yours.
Hi, thank you, Norshan. First of all, I would like to thank you and the SNT Conference Organization Committee for giving me this opportunity to take part in this panel discussion. So I'm Guillaume Doucet, as you said. I'm presently working at CEA, the French Atomic Energy Commission Military Application Division. CEA is a large public research organization with a bit more than 16,000 employees. The R&D covers a wide range of fields from, for instance, fundamental and applied physics, microelectronics, biology, medicine, and sustainable energies. Our laboratories are located about 30 kilometers south of Paris. Myself, I've been working in the field of nuclear instrumentation for a little bit more than 20 years. I started in the field of plasma diagnostics, then I moved to radiotherapy instrumentation, and then to low-level environmental radioactivity monitoring. So basically a quite big gap from terabecquerels down to millibecquerel metrology. Right now, I am in charge of the French IMS accredited. I have been in charge of the French IMS accredited support laboratory, and I'm currently heading the radionuclide part of our national data center. I took part some years ago to the development of the SPALAX NG next generation, and to some other advanced detection system. I will try to start my presentation now. If you see it, is it okay?
Okay.
Okay. So first, I would like to start with a look back at the last 25 years. The idea is to try to know when we try to know where we are going to, I think it's often useful to remember where we are coming from. So I propose first a quick look back at the last 25 years. Two radionuclide technology have been approved for nuclear test monitoring during CTBT negotiation. Both aim to detect the ultimate proof of a clandestine nuclear test, the presence of a fresh radioactive fission product in the atmosphere. There are two kinds of radionuclides. The first one are the radioactive aerosols, often referred as particulates, and the noble gases, which are mainly radioactive xenons. In the case of an underground nuclear test, which is supposed to be the most likely scenario in the case of treaty violation, a simple calculation shows that the expected atmospheric concentration at the station level are in the range of a few tenths of microbecquerel per cubic meter for aerosols and a few millibecquerels per cubic meter for radioxenons. So 1 becquerel means 1 disintegration per second, and usually much less than 1 count per second at the sensor level. So this means it's a very low signal. This means that the detection system should be able to process large amounts of air to get a decent signal while being able to achieve a very low background. Another constraint that we have is the sampling period of the station. It must be short. Short means less than 1 day, less than 24 hours, to be comparable to the time it takes for the plume to go over the station. In the framework of the so-called INGE initiative, several nations, namely USA, Sweden, Russian Federation, and France, started the development of low xenon detection system in the mid-90s. Very clever systems implementing different technical solutions have been designed within a few years. They were assembled and tested. The systems are the ARSA, where the ARSA, the sonar, RX, and the SPALAC systems. And most of them are still operating today on the IMS network with great success and high availability. On the particulate side, in order to achieve a microbecquerel per cubic meter sensitivity, high flow rate samples have been designed. Again, the CTBTO encouraged the manufacturers to invent and develop optimized systems to offer high performance while being able to operate at the most remote sites. Today, 4 systems are operated, the Finnish Cinderella and Snow White systems, the American RASA system, and the French TGT system. Once again, the availability of these systems is very good, and the IMS network is now nearly complete. So what can be the future? First, maybe we can start with the xenon systems. At the beginning of the network, the very first feedback from operation of the xenon station in the early 2000s was the discovery of radioxenon background that was much higher than initially expected. It turns out that most of it is coming from medical isotopes production facilities, because uranium targets dissolution process that are in place in these factories can release up to 1 terabecquerel per day of xenon-133, which is in fact not so far from the magnitude of underground nuclear test release. Fortunately, the signal due to this background is predictable, as you can see on this moving map. It depends only on the source location, which are well known usually, and on meteorology. The isotopic signature also differs from the one of a nuclear test, especially when one considers the metastable isotope of xenon. And we can use this well-known Kalinowski plot to sort out between the military and industrial signals. I think 2 main axes might be followed for the future. First, the new measurement systems. The next-gen systems are currently under development. They all aim at improved performance for detection sensitivity. They are typically close to 0.1 or 0.2 millibecquerel per cubic meter for the 4 relevant isotopes. This means the improvement is larger than 1 order of magnitude compared to existing systems. The manufacturers also worked on the reduction of the sampling times. We went from 24 hours down to 8 or even 6 hours, because better time resolutions means more accurate signals and better source localization. These new systems, namely the Sonatry, the MIX, the Xenon Internationals, and the SPALAX NG, will be deployed on the IMS after formal acceptance. This will take place over a period of 15 to 20 years starting from now. If one tries to think beyond that horizon, I think the way to proceed might be to work on electrical consumption, footprints of the systems, and cost, of course, while preserving or even improving the performance. The reason is, after entry into force of the treaty, discussion will engage on the IMS extension from 40 to 80 noble gas stations. And I think if it is accepted, then this will enhance dramatically the detection capability of the networks, but the points highlighted above will be particularly important. The second axis to work on is the knowledge of the industrial xenon source term. As you have seen on the map before, few medical isotopes factories are producing the largest part of the background. There is a project which works on a voluntary basis that has already started. It's aiming to monitor the release of the factories directly at the stack level. Implementing those signals in the IDC database, I think, will help quite a lot to understand the detection. And finally, if we consider the longer term future, I think accelerator-based production of Molly-99 could one day supplant maybe the fusion-based production and then greatly reduce the civil xenon background. If we think to the aerosols, on the left of the slide, you can see the principle of current samplers. So the systems are relatively basic. The air is sucked in through a filter by means of an electrical pump. So this system, it is very simple, but energetically, it is quite inefficient. Typically, the system needs about 10 kilowatts to sample, let's say, 900 cubic meter of air per hour. So if one wants to increase this flow rate and push the detection limits further down, larger filters and larger pipes are needed. It means even more power. Thus, I think the 24,000 cubic meter per day or per sample is kind of a glass ceiling with the current technology. If one wants to go one step further, one would need to revisit, one idea would be to revisit the industrial principle of electrostatic precipitators. These devices are well known in the industry. They are used to purify large amount of air or fumes with high aerosol contents. Filter papers cannot be used in this case because they will be clogged very rapidly. So the principle of this device is basically relatively simple. The aerosol and the air is sucked in by a standard low power fan. Then the aerosol are ionized and collected by a static high electrical field. The particulates are collected or precipitated directly onto the electrode. So the nice thing is that there is almost no resistance on the airflow. So thus the power requirement of this system is drastically reduced, and the flow rate might be very, very large. For instance, in Paris, there is a subway station which is fitted with such a system. This system is able to filter up to 50,000 cubic meter of air per hour. This would be, of course, a kind of a dream for our CTBT field. More realistically, I think 5,000 to 10,000 cubic meter per hour seems to be reasonably achievable, and this would enhance immediately our performance by a factor of 5 to 10. As mentioned earlier today, our colleagues from the US already explored this possibility and published a study on this application in 2019. One can also work on the detection part once the filter is collected. So in this field, I think the gamma spectroscopy technique can be improved quite a lot too. This, thanks to the development in digital electronics, one can do some gamma-gamma coincidence or gamma-muon anti-coincidence setup that can be developed without large efforts. So the idea is to put to sandwich the sample in between two germanium detectors. Several studies have shown that in some cases this technique can push the limit down maybe as much as 1 order of magnitude. For instance, is shown on this slide a weak cesium-134 signature that will be buried in the baseline of a standard spectrum of a fresh aerosol filter. Then if we go to coincidence mode, the signature shows up immediately on essentially a zero baseline. Of course, one can also, I think, to implement even more sophisticated state-of-the-art detection system at the level of support laboratories. So if we combine this very nice detection system with very large sampling flows, we can imagine that in a few years, the sensitivity of aerosol system can be improved drastically. And the nice thing with aerosol, as opposed to noble gas, is that their background activity is very low. So in my opinion, there is still plenty of room to improve further the capabilities of the radionuclide IMS stations. And for sure, these technical challenges are very exciting. And I will end with a final thought. If we refer to the history of techniques, I think we are perhaps today on the eve of the invention of the microscope. Both aerosol and for radio xenon, there is maybe a new horizon to discover with this new system. We could believe that better detection sensitivity will solve of all of our problems. In my opinion, it is only partially true, because new capabilities also means more detections, more questions, more challenge to understand what we might detect. However, I think ultimately this is going to reinforce the treaty's verification capabilities. And that's it. That's what I have for now. And
thank you very much, Dr. Doucet. It was almost the common subjects we have. We have been cooperating a lot with CAA also. Thank you very much for this. We have been working many common projects with them. Thank you very much. These are all important points, particularly in noble gas and particulate monitoring system. We have been trying to also enhance our sensitivity. Since we have not much time left, then we would like to ask only one question to all panelists. Considering a mid to long-term time frame, what you may see as disruptive or game-changing technologies for the international monitoring system. I would like to collect your answer just within 2-3 minutes only, because we have not much. We have only some minutes, I think. We can, again, the same order, we can start from Kodaira. I think he is almost sleeping.
Some of them may
Japan is
already.
now, yes.
Yeah, it's almost 2 a.m. Okay, thanks very much. So first of all, I have to tell you, I'm not expert of CTBTO monitoring. I'm marine seismologist. So in the sense of marine seismology, which may be somehow related to CTBTO, I think the kind of new monitoring technology which we are developing are such as sea-flow optical cable sensing, including fiber optic tiltmeter and also a DAS system. I think the JAMSTEC is a marine earth science institute, so we have some expert of instrument development, but the most of scientists in JAMSTEC is a geophysicist, and the one of the advantage of our institute is to evaluate the data observed by a new technology. And recently we deployed our fiber optic tiltmeter and also DAS system. We found that this is very sensitive and good quality data we can acquire using those techniques. So, for example, tiltmeter is almost equivalent of the broadband seismometer, and that means we have very big potential to monitor the wide spectrum ground motion, and the signal to noise ratio is quite good compared to broadband seismometer. And also the fiber optic DAS technique is, I think, again, I think there is a big potential to monitor the wide spectrum of the ground motion and also hydroacoustic signal. The important, I mean, strong point of those system is number of stations is dramatically increased using fiber optic cable. That means we have big potential to apply many highly sophisticated signal enhancement technique. So this is most important things we have to challenge in the next couple of years. So that is what I'm thinking right now.
Thank you very much for that. Yes, fiber optic cable also important. We have been also trying to change, re-establish some of them as hydroxide station, new fiber optic cable. Then Professor Waxler, we would like to hear from you also.
Yeah, I have two things to say. Large N, so what that means is replacing the single sensor elements at the arrays by a mat of closely spaced, less expensive but reliable sensors. I think that's the only way I can see to beat the wind noise problem. And the second thing is in reference to Thomas's presentation, which I like very much. I think it's critical to develop infrasound reference sensors that are tied to an international standard and that are traceable and that are calibrated before use and after use. I think that's critical, and I really appreciated Thomas's presentation. Thank you.
Thank you very much. Dr. Bruce?
Yeah, actually, it's a little bit like tennis between Roger and me. Large N is also on my radar for that. If you look again at industrial application and the closer metrology community, there's a large fight currently going on with sensor fusion, data fusion, sensor networks of the same sensors in a spatial distribution, or different sensors sitting close together but giving complementary information and making use of that. And the biggest difficulty that we face in the metrology area is to find such networks, to find examples, to get people running such networks online with us and having them using harmonized data formats and all those practical issues. If I look into the CTBTO or the geoscience community, on the other hand, this is all clarified for decades, is my impression. So you have a harmonized data system. You have your international data centers with, or national data centers with availability of decades back of data. So you have all you need for training neural networks and artificial intelligence systems, deep learning, big data exploration, and all this hype stuff that is currently underway in metrology research. And I think that those developments, if used properly, will be a game changer in the future, not only for you, but also coming from your community for others. Of course, being a metrologist, I think proper calibration and the propagation of uncertainties in these systems is crucial. And we saw that already in industrial networks. If the sensors are not proper synchronized and calibrated, a neural network can make all kinds of guesses, but nothing that has really makes sense. So again, large N is probably, if you use it correctly, it's probably a game changer.
Thank you very much. Since our technical specification also very unique, then we are also, it's important for us to calibrate all the equipments properly to get the same measurement. Okay. Dr. Jeffrey, we would like to hear from you.
Well, thank you. I will keep this short. I actually feel that Kadaira-san made a very good case for distributed acoustic sensing or distributed Rayleigh sensing, however one wishes to describe it. I feel that the CTBTO trunk cables, having almost certainly unused optical fibers there, are begging the scientific community to use them with acceptable interrogators, and then they will form in their own right a large N network of linear sensors there that could be taken advantage of. So I would be excited to see that being pursued. Thank you.
Thank you very much. Dr. Gülüyor?
Sorry, I missed the
Yeah,
sound.
thanks.
Thank you again. Just a final word to say that we heard a lot of new technologies that might show up someday on the IMS. Maybe a point that we shouldn't forget is that the IMS network is basically an on-site system. We are not in a laboratory. This means that we have to have systems that are first quality is to be robust, and we have with large data availability. It's always better to have low quality data than no data at all. So we shouldn't forget this idea, I think. But thank you again.
I thank you very much. I think I can take some questions if you have coming from audience. Jeffrey, one question comes for you. How far along the fiber could you retrieve information? How far is the further heterogeneity? What are the main challenges, solutions to push this limit?
That's an interesting question. Commercially, there are a number of companies making distributed Rayleigh sensing systems out there at this point. But the commercial limit right now seems to be 50 kilometers, although I understand that OptaSense will shortly be officially announcing a greater distance than that. So at least 50 kilometers. One of the problems being you can only send so much light into the fiber. If you put higher intensity light into the fiber than a certain limit, you start getting some nonlinear effects that swamp the signal that you're trying to retrieve. So at this point, I think 50 to 100 kilometers is the maximum range. And the longer the range, then typically the longer the gauge length, the individually addressable segments of fiber.
There is one more question. Does infrasound directly affect seismometers? Or does infrasound creates ground tilt, which creates seismometer noise?
Yeah, seismometers pick up infrasound if they're not too deep in a borehole. And sometimes, very often, infrasonic signals picked up on seismometers are used for scientific purposes. So the answer to that is yes. Was there a flip side, another part to that question? I didn't hear.
Do they affect the seismometer directly, infrasound, or does infrasound create a ground tilt, which creates noise for the seismometer?
It shakes the ground, which the seismometer then picks up. In the air, I'm not sure if the seismometer would detect it directly or not. I know that in the ocean is a robust medium, sufficiently robust so that seismometers can be used as hydrophones. But in the atmosphere, I'm not sure how sensitive a seismometer by itself would be to infrasound.
One more question I would like to ask, also it's coming from audience. What about the transfer function DAS measurement? What associated metrology?
Pardon, I did not get the detail of the question. Can you repeat it?
I can repeat it. What about the transfer function of DAS measurement? What associated metrology?
The transfer function of what? Sorry.
DAS.
I think it's distributed acoustic sensing, and I don't have an answer for that one.
The sensor measurements.
Yeah, I don't have a good answer for that one. I think it really depends on what physical parameter you're measuring, and I believe a fair amount of that stuff is buried into intellectual property from the various manufacturers, but I'm not sure about that.
I can at least state here that we did for example, in the Force laboratory, did calibrations and investigations of fiber optic strain and therefore force sensors embedded in concrete, for example. So there have been investigations, but I was not directly involved in that. So I'm sorry to have no details.
Okay. I thank you all of you and also audience for your participation and engagement. It was really, I'm very pleased and honored. We all are pleased and honored to have you today and hear from you. It was very interesting for me also personally and for all the others and for the audience. Very interesting presentation. And I'm going to think about the Rogers also suggestion, recommendation, if it seems impossible for the auxiliary infrasound stations. Thank you very much to all and good evening, good night. Thank you again for your participation and your support.
And thank you for the invitation. It was an honor.
You're
Thank
welcome. It's our pleasure.
Thank you very much.
Very much.
Thank you. Goodbye.
Or good morning, Kodeira-san.
Good night, actually.